let's do another one of these. Let's go back again to the day that we had looked at flux before. So previously, I believe 3 class days ago, we found the flux of the vector field F equals z comma y comma x across the surface, specifically across the sphere, capital S, and capital S was described this way. It was x squared plus y squared plus z squared equals 49. And what we did, just to remind you, we did this by parametrizing the surface S as r of u comma v equals, and we did this inspired by spherical coordinates. Yeah, so we did like well, rho would just be fixed to be 7, right? Because it's going to be the radius of the sphere. So it was like a 7 sine of u cosine of v. So I can already see that. I'm just trying to remember. U played the role of a phi coordinate from spherical, and v played the role of the theta coordinate. Okay, and then 7 sine of u sine of v, comma 7 cosine of u. I'm just trying to put in some reminders of what we did. It was quite a lot of work. There was a lot of pieces, but eventually we got the value of the integral over S, that was the region of integration, and the thing that was integrated was f dot n ds. So in other words, when computing the flux, we ended up with, and I want to remind you, we got 7 cubed times 4 pi over 3. And it was a lot of work. There were a lot of steps. It was good that we did it, don't get me wrong. It was a little tedious, but it was good to do it as a practice of just computing flux while that was new. But it was tedious, and we're going to revisit the question and have, again, the double integral over the surface of f dot n ds. But instead of computing it directly, we're going to say, you know what, using the divergence theorem, this will be way nicer, way easier. It will not be tedious at all. The divergence, so we'll use the divergence theorem. So S itself happens to be the boundary of a three-dimensional region E. What is E? It should be the solid sphere, or the solid ball is really the word that's actually used, right? So E, just to describe it first in notation, sometimes this makes it easier for people to spot what we're trying to talk about. X squared plus y squared plus z squared less than or equal to 49. So the sphere itself over back here was with an equal sign, but now if we have a less than or equal to, I hope you're seeing what I mean by the filled in thing, right? So it's like there's the shot put, all of it, filled in on the inside, even the part we don't see, filled in with metal, versus the peel on the outside, right? So E really is the solid ball of radius 7. And the boundary is S, is the sphere that we dealt with in the previous problem, back on the other day when we were first looking at flux. So here's the thing. To use the theorem, we're going to need, so we know what E is. Okay, it's a solid sphere. We need the divergence. Well, the divergence of this vector field, right? So divergence will be the dot product. So we've got, just as a reminder, partial derivative with respect to x, partial with respect to y, partial with respect to z. I know it's a little funky to call this a vector itself, but it just helps as far as remembering all of the pieces. Then we need the vector field. It's up here, z, y, x, huh? Okay, so z, y, x. Well, when we dot, we're taking the partial derivative with respect to x of z. That's going to be 0. The partial derivative with respect to y of y is going to be 1. And then we need to add in, remember this is going to be a scalar when you dot product, partial derivative with respect to z of x, and that will be 0. Yeah, so we end up with really just 0 plus 1 plus 0, just 1. Okay, that's real nice. So actually, the original question we were asked, which was to find the flux, right? Instead, due to the divergence theorem, is the triple integral over the solid region E of the divergence of f dv, whether this dv is dx dy dz or dz dy dx or dy dx dz or whatever. I'm going to advocate we don't use any of those because really this is the integral over e of the divergence of f gets replaced with the 1 that we just computed. So I'll have a 1 here, dv. And guess what? Due to the shape of e, right? E is the solid ball of radius 7. Of course, you could write this in rectangular coordinates, right? You could say this is a dx dy dz, or perhaps actually preferable to have a dz dy dx, so you could project onto the xy plane. Actually, isn't this going to be nicer if we don't use xyz coordinates? Of course, you could do this in cylindrical coordinates, but even nicer than that, wouldn't it be nicer to just do this in spherical coordinates, right? So integral sign, a little bit of space between the integral signs here. There's that Jacobian for the spherical coordinate integration. So rho squared sine phi, d rho d theta d phi. And so rho on the inside, it's the entire solid ball. So let's see, rho starts at 0 and ends at 7. Theta goes from 0 to 2 pi, and phi goes from 0 to pi. Now, we've worked through integrals that look like this before. The point is it's not bad. I mean, the fact that it's rho squared times a sine phi means ultimately, morally, you can split this out, factor out if you want. You've got a rho integration separate from a theta integration, separate from a phi integration. This is not a bad integral at all. We will not go through all the work right now. I'll just mention that if you go through it, you will get 4/3 times pi times 7 cubed. You should really do it because it's not a bad integral. But the point is, we get as a final answer here the same number that we got back here, the original way last time. But the point is that this is much nicer. This is much nicer than parametrizing S and doing all the work that we did last time. Again, don't get me wrong, we needed to do the work that we did the previous time. It was on its own an excuse to just practice setting up the integral, however tedious it was, for computing the flux in a direct manner. But the point is, I picked that problem specifically way back when, knowing that it'd be nice to come back to it and get the same final answer using the divergence theorem.